Okay, in this video is a brief overview of a tool called FTKImager, and it runs in Windows. And you can download it off of Access Data's website. It's a small program, and it's separate from its larger cousin, which is the Forensics Toolkit, which is used for analysis and examination. The FTKImager does a few things, and it does it fairly well. It can create an image of a physical or logical device. It can verify that image with a hash, and it can be used to do a quick physical analysis, that is looking at the physical level and actually the logical level as well through a list of files. But if you really want to do a full-blown examination, you're going to want to do that in the Forensics Toolkit, which is a commercial product which costs several $1,000s, and it requires a hardware dongle. There is a demo version of the Forensics Toolkit you can download, and it can access up to 4,000 different files. So that's something that we'll look at later on, but right now we're just going to be looking at Imager. And for this, what I've done is I've chosen a very small, actually I got a couple here, USB thumb drives. This is 128 megabytes, and the reason I chose small ones is because I have them available from years ago. It doesn't hold a lot of information, but we really don't care about what's on here, but because we're just going to be looking at how this tool works. And I have a Swiss Army knife that has a 64 megabyte capacity, which is ideal. So if you want to do something like this just to play around with it, it's good to have something small. I guess you could get those on eBay, or if you've got an old one, go ahead and just use one of your old small USB devices and FTKImager to take a look at its contents to create an image of it, which should be very small, and to verify that image and look at the physical and logical contents of the media. So let's get started by going to All Programs, and this isn't going to show up on your screen, but we're going to All Programs, Access Data, FTKImager folder, and then FTKImager, which opens up the program, and it asks us if we want to make changes to the drive. And what that's doing is it's not as you'll see, it's not allowing any thing to write out to your destination media. However, once you plug in your media, there is the opportunity for the operating system to write out to it. So that may supersede the fact that you've even opened up FTKImager. There's nothing you can do about that unless you use the hardware write blocker. And I've got my USB thumb drive in my computer, and this is the FTKImager interface. Notice it has 4 quadrants here, and as we walk through this exercise, you'll see what is contained in each of these quadrants. If we want to go to File and Add Evidence Item, notice that it has 4 different options here. Since we're working with the physical drive, we want to select that, but also notice you can look at the logical drive, or you can open up an image file if you've already created an image of your media. We'll select physical drive, click Next, and this is where we get to select our source. Notice there's 4 sources here. If we go down to the bottom, notice it says Memorex thumb drive. We click Finish. Whoops. Select it. There we go. Memorex thumb drive. Click Finish. And we see some of the quadrants have been populated now. Notice up in the upper left-hand quadrant, if we click the plus boxes, it shows us our physical drive. And if we click on, here's the volume name, and now all the quadrants are populated. You note that in the upper right-hand quadrant, this tells us that there's a root directory and the size. Notice the unallocated space. It hasn't recovered any of the unallocated space. That's usually not something that is done here in Imager. That's done in the full version of FTK. Notice it says that we have 2 FATs. Now if we look down here, after we've selected FAT 1, if we look down in the lower right hand quadrant, we see it does have FAT information. Recall that the F8 means that this is a hard drive, although it really isn't. The F0 here would mean it's a floppy drive. F8 really means anything else. The FFFs, the two FFFs here, or actually the three, indicate what is used to indicate an end of file. And then we see 3 and a 4 and a 5 and a 6 and a 7, and that indicates that whatever the file corresponds to in the root directory is taking up these locations. And these are the logical cluster numbers, 3, 4, 5, 6, 7, 8, and so on. Notice the FF combination right here is going to symbolize an end of file. If we go up here to FAT2, we see that it has the same exact information as FAT1 for redundancy purposes. Some file systems reserve certain sectors for system information. You see that 4K, which would be 8 sectors, have been allocated thusly. Then you select the VBR, which is volume boot record. Since there's a single volume here, then the mastered boot record will coincide with the volume boot record. And so, if you've taken my other classes, you know this is a master boot record. What it was formatted with, notice that when you click on the right here and you select something, it shows correspondingly what it looks like in hex. Notice that although the volume label says no name, if we go down to the root directory, it will indicate what the name of the volume is. Notice this FAT16 formatted file system. And if we move down to the end, right before 200, there we go, 200 will be next. Notice that the 55AA always indicates the end of a master boot record or volume boot record. Let's go back up here to the left-hand quadrant, upper left-hand quadrant, and now we get a logical view of our file system. Notice that there's 3 files on here. It looks like 2 graphics and 1 text file. When we click on the root directory entry, it shows us the root directory. Notice that we have 4 entries in here. And so the first one is going to be the volume label. Notice there's the DSC ping, snort.txt, and SE ping. Notice each one corresponds to 2 lines. If the file names had been longer than the 8.3 naming nomenclature, then this would take up more than 2 lines, because then you would need a long file name. And so then each one of these would take up 2 entries, or 4 lines. Let's go and select DSC ping, and we can do a quick logical analysis. You can see this is just like any file browser. You can see the contents of the files. Notice in the bottom left-hand quadrant, it tells us the properties of the files. Here's the name, what type of file it is, the file size, the physical size, which will always be no smaller than and usually larger than the file size. So there's going to be some file slack in there in between the end of the file and the actual number of sectors that comprise the file. The starting cluster, the date created, modified, the date last accessed. Notice the date last accessed doesn't have a time associated with that. And we'll get into more of that. Actually, we have covered some of that in the FAT file system, but you'll see that on the FAT systems, the date last accessed will not have a time associated with it if it's a FAT. In the 8.3 short file name, what type of file it is, and so on according to its DOS attributes that can be found in the root directory. In here, remember the DOS attributes. If we go up to the physical drive and select that in the bottom left-hand quadrant, it tells us a little bit about the physical drive, what type of disk it is, number of cylinders, tracks, and so on, number of bytes per sector, which is generally what it is, 512 bytes. The sector count, 258,048, and that the model is a Memorex thumb drive, USB device. Okay, let's go up and look at some of the other modes here. The FTKImager has a light version that you could fit on a thumb drive, so you could walk in and pop that into a running computer and capture memory if you would like. So sometimes there is information that is kept solely in physical memory, for example encryption keys, and you may want to access that information, and one way to do that is to capture running memory in RAM. We can look at capturing protected files, which we'll cover a little later on. It detects whether there's EFS encryption involved in the volume. We can also export individually each of these files as well as the hash of each of the files, or a directory listing, and you can try this out all on your own. It's fairly simple to do. If we go under view, we've kind of already seen all this, and it's something that you can look at on your own because we've looked at the properties in the file list over here in the evidence tree. And then you can look at the mode, which shows up down here in the bottom right hand corner, whether you want text only or hex or the combination of the two. This will be considered the text over on the right hand side and the hex on the left hand side. And of course there's icons corresponding to everything under the file menus. Okay, so let's go back up here, and what we want to do is we want to create a hash of our drive. And so notice that there's many options up here. We can remove this evidence item, we can verify this drive or image, and we can also create a forensic copy, which is what this export disk image is. Let's go ahead and let's verify it first. And notice that it starts automatically. It's guessing this can take about 2 minutes to verify it. And as you'll see shortly, it creates two different types of hashes, an MD5 and a SHA-1. That's a secure hash algorithm. And let me pause the video and then we'll jump back here after it completes. And after 2 minutes it's finished. Recall the sector count, 258,048, that's correct. Notice that it created two verification hashes, an MD5 and a SHA-1. And this is something that we want to copy and paste, and I'm not sure if you can copy and paste it. I guess you can't. And right-clicking doesn't do it, so you'd want to create a screen capture of this. I'm not sure why I won't allow you to do that, but I've written these numbers down. And then there's no bad sectors. So we've created the hash, and now what we can do is to create a, let's go back up here, physical drive, right click, and we want to export a disk image. This is our image source, physical drive 3, which is our thumb drive, image destinations, and here's 4 different categories, 4 different options. The raw is a DD format, so it just takes the raw data. Every forensics suite or program should understand the raw data, so when in doubt, use this. SMART is a Linux-based forensics tool suite, and I'm not sure exactly of the format, but that's going to be a proprietary format, and so it may or may not be able to be read by other forensic suites. The E01 is an encase format, which adds additional information after every 64K it reads. It creates a hash of that 64K, so if there's some type of corruption between the original and the image, you can go back and tell where the image was corrupted. And then there's the advanced file format, which is an open source format which can be extended by others. And so the only one in here that's really universal is the raw. And so we'll select that, and then we can provide the case number 002, unique description, imager, example, your name. Click next. Wants an image destination folder, so let's create one on the desktop. call it Imager example. Click OK. The image file name, we'll call it Imager example. Okay, the image fragment size. Some software allows you to write out images in small sections or partitions or fragments, and in most cases you won't need to use these fragments. So notice that it says for RAW, the in-case version, the advanced file format, do not fragment. I'm not sure why that's not set to 0 automatically. And you can provide encryption if, for example, you're going to be sending this over a network somewhere or it's highly sensitive information. We can click Finish. We'd like to verify our image after it's created. And let's go ahead and create a directory listing of all the files on the drive since it's only 2. We click Start. And let me pause this while it creates the image. And the image was created. It tells us the name of the image, the sector count, which is correct, the computed MD5 hash. Notice it computed it, and the reported hash so it essentially does it twice to indicate that it does match. And the same thing for the SHA hash. So it does a before and after, and there's no bad sectors. So we've created our, we can close this. And now let's go to our desktop, our Imager example. And the files are here. This is our raw file, our DD file. We can open up this file, and this tells us the contents, the physical contents, essentially the logical contents, volume boot record, the size, the reserve sectors, the FAT and how large it is, and the sizes of the files, and the total size, as well as the created, modified, and access times. Let's close that, and if we open the text file, we'll see that it has a lot of detailed information about the case that we put in, the drive geometry, the physical drive information, the computed hashes, and we know those matched, the image information, when we started, when we finished, took about 2 minutes. The segment list, in this case, is just a single file since we didn't segment it, and the image verification results, and you see that it matches. Let's close that and go back to FTK. Let's remove this evidence item, and let's go back and let's add that image. Browse the desktop to Imager example. It's our DD file. Click Finish, and there's our image. So that shows you very quickly how FTKImager can be used to create an image, how to verify your image, and how to do a quick physical and logical analysis on your media.